These are the video notes for section 11.2 and 11.4 on the ellipse, second day of conics. The ellipse is created by slicing the cone with a plane that is at a really slight angle. So for example, if that plane was parallel to the base, we'd actually have a circle here. So just a little bit of an angle creates our ellipse. All conics have pretty good applications, and so we'll talk about some of them today. We'll do a little bit of word problem at the end. So our theme today is going to be the same as parabolas. So we're going to go through discussing the equation, then sketching graphs, then equation writing, then word problem. So we're going to stay in that theme throughout the days of talking about conics. So let's just walk through some of the visual stuff and things you can think about that would be related to ellipse. Planetary orbit is always a good one. So the planets around the sun have an elliptical pattern because the gravitational pull is stronger in one part of the orbit than is in the other, creates that elliptical pattern. We also have orbital patterns that could be parabolic or hyperbolic. And that would be, for example, something that comes into the solar system and leaves, but it still follows a path. So that would not be elliptical. The elliptical machine, so probably all familiar with that. The reason, if you ever thought why it's called elliptical, let's just look at an image here for a second. It has to do with the body motion. So as you see this in a minute, you'll see the image here as you watch the knee of the guy on it. As soon as it kicks in, there we go. If you were to trace, like if you could put like a pencil or pen right on his knee joint and you could trace the knee motion, that's, I'm trying to do it here, but he's moving pretty fast. That's an ellipse. So that's the reason it's called elliptical. Also, what's different about elliptical than some other exercise machines, that the very low impact, very low stress in your body. So there's no pounding motion like running. So it's for people who's, well, some people just like the machine, but also some people use it because they need the low stress in their joints. Elliptical architectural design ideas. Elliptical domes are pretty common. Elliptical arches. There's a unique thing going on with an ellipse, which we'll talk about in a second. But I'll tell you what, let's do that right now. Then we'll go back to the idea of elliptical dome. So every day we have kind of a geometric definition. And this one is related to how the foci distances from a point in the graph are related to the major axis. So we'll talk about the major axis in a second. But the basic idea here is that the two red lines added together would equal the length of the major axis. Now, ellipses having two focal points, there's something unique in terms of sound going on here. So at the state capitol and the U.S. Capitol, there are elliptical domes inside the main halls, and there are actually spots probably marked on the floor. I don't know what they're marked with off the top of my head, but if you stand at the exact focal points under the elliptical dome and you speak, your voice will travel to a point on the graph, to the point, excuse me, on the dome, and then it'll bounce off and it'll travel back down to the other focus. But you got to be standing at the two foci. So if you have a person here and a person here, it's called a whispering room. And if you don't have like 100 people in there in the background making a bunch of noise, you could stand at this spot, your friend at this spot, and you could talk in a really low tone of voice, and they would easily hear you because the sound would be directed right back to that spot. So kind of an architectural, interesting idea based on elliptical dome and having the two focal points. Okay, let's get into talking about design a little bit. So you got two kinds of ellipses. You got a horizontal ellipse and a vertical ellipse. The long axis of the ellipse is called the major axis. The short axis is the minor axis. We have two focal points now, so we'll say foci. Some people say foci. I like to say foci myself. And then some of the distances we need to know. So this distance from center to foci and center to vertex, and then center to a name we don't have for this actually, but what are those called? So we label those with some letters. Center to vertex is our A distance. Center to the edge of the minor axis is the B distance, and center to foci or focus is the C distance. And so the major axis then is 2A, which means vertex to vertex, minor axis 2B. And then we've got a specific way to find our C by calculating it in comparison to A and B. Looks kind of like the Pythagorean theorem, but turns out it's not, right? But it's a C, we just call this the C-squared equation. And so when you have an ellipse, the C-squared equation is what you use to calculate the value of C, distance from center to focus. Okay, let's break down the equations a little bit for the purpose of graphing. So really what you got to be able to do is you got to be able to determine which type you have based on the equation itself. And by type I mean, is it horizontal, longer horizontally, or is it vertical, longer vertically? And the way you do that is pretty simple. We look for the larger of the two denominators. So the larger of the two denominators will always be our A squared value, which will produce A, and that's always going to be the distance again from center to vertex. So that would be our major length. So here's how it works. If you have X over the larger denominator, or I just think of it as X over A, then X is the major axis. On the other hand, I'll switch to the other equation here for a second. If you have y over a squared, or y over the larger denominator, then your ellipse is going to be vertical. So this would be your a distance, center to vertex. And that's really kind of it. That's how you distinguish the two. So you just look at the two denominators and then you do a comparison. You go, well, where's the larger denominator? What's it under, or what's it attached to? Another way to think about it. And so if A is attached to X, you're looking at a horizontal ellipse. If Y is attached to, if A is attached to Y, then you're looking at vertical. And that's pretty much it. And then again, the c-squared equation will help us do the focal points. So we're going to go ahead and run through a couple of graphs, then we'll do some equation writing, then a little bit of word problem. One last thing that every day kind of has sort of its own little unique thing going on. Like you talk about when parabolas, you got directrix. It's kind of this sort of thing like, what is that? What does it do for us? Doesn't actually really help us draw the graph, but we do graph it. Ellipse is kind of a weird, unique thing. It's called eccentricity. What it is a relationship of C to A, so it's a ratio of the focal distance to the major axis, or to the distance to the vertex, I should say. And what it tells us is how elliptical our curve is going to look, our sketch is going to look. So if this number is closer to 0, your ellipse is starting to look almost circular. If it's close to 1, then it's looking pretty elongated or stretched out. And that's about all it does for us. It's not important to draw a graph, but we'll use it sometimes in equation writing, and you need to know, what it is. So there we go. All right, let's get after it here. Oh, and then shifted, of course. So, we talked about shifted with parabola, and it's no different here. You now have a center at 0, 0, so that's not a vertex anymore. That's a center and an ellipse. And so if we shift, H and K doesn't change much of anything, doesn't make this harder to do at all. You just are now going to operate from a different location than 0, 0. That's it. So you can see X minus H and Y minus K inserted into our equation. And that's nothing new for you guys. We all know how to do our shifting. Okay, so we'll start with a no shift, and then we'll do a shift with basically the same numbers, but just give us a different location. So first thing we want to do is recognize what type we have. The fact that this is the larger denominator and it's attached to X tells me that it's horizontal. And then that means 25 is my A squared and 9 is my B squared, so there's my A and my B. C by calculation, so I'll just do a quick calculation for that. We'll do the square root, A squared minus B squared. Pretty simple stuff. And then what you guys want to kind of get used to again is trying to do the list of stuff without actually seeing the graph. So knowing it's horizontal, that means the vertices and the foci sit on the x-axis. So that means I know that these are going to be the case. Then eccentricity C over A. That's 0.8, so that's closer to 1 than 0, so it's going to look more elliptical. Okay, let me pop up the points for this so we can see our first graph. So there's our center. We can travel out 5 and 5. Foci don't help us draw the graph, but you can certainly plot them. And then the B distance, 3 and 3, and then draw your ellipse. Pretty easy to draw. When you go to shifted, it, like I said, doesn't really change much of anything in terms of the work. You got a center that you're going to have to pull out of here, so your H and your K. So we got our center coordinate. And then again, think about being able to do this stuff without actually sketching the graph, even though I know that the distances are still going to be 5 and 3. And I could do it. I could go 5 and 5 and 3 and 3, and I could do all that. 4 and 4, excuse me, or 3 and 3 this way. But if I think about the fact that all these coordinates lie in the same horizontal line, then one of the two parts of them has to be the same, which would be 7. So I can tell you that every single coordinate has something comma 7 going on. Then from -4, so now we're looking at, here is -4. How would I get to my vertices? Well, I would go 5 and 5, all right? So I'll subtract 5, like -4 minus 5, -4 plus 5, and there you go. And then foci, same thing, but this time I would be doing 3, so -4 minus 3, 4, whoops, the C distance, and then -4 plus 4, which put me at 0. I didn't plot them this time. Again, we don't need those to draw the graph, but I will do our B distance, and there's your ellipse, shifted ellipse. So again, shifting pretty easy to do, doesn't really make it more complicated. One more graph, just so you guys can see another round of this, like some other little things we can do, but pretty easy to graph. It's just kind of getting used to, again, what the equation is telling you, which is true for all kinds of graphs that we do. So if it doesn't read equals 1, you need to do that. It has to read equals 1, so there'll be a quick little divide by 32. Now I just going to look at my bigger denominator, which is attached to y, so that means we're going to be vertical, so y over the larger number. That means this is my a squared, this is my b squared, so we'll go get our values here. C squared by calculation, just leave it as a simplified root, that's fine. And then because it's vertical, that means that my vertices and my foci sit on the y-axis now, so we'd have that. And then a ratio of C to A, and that's still closer to 1 than 0 by far, so we're going to be looking more elliptical. So again, pretty simple. We'll do a little bit of counting here. And then 2 root 3 is about 3.4-ish, or so, about 3.4, right around there. And then my B distance 2 and 2. And draw my ellipse. So again, super easy to draw. Okay, and then shifted idea, right? So we would take this equation, also divide through by 32. So we do that quick. We grab our center out of there, so h and k. And then again, same idea, right? I should now be able to do this stuff without ever seeing the actual graph, even though, of course, you know, you guys can graph it first if you want. But I should be able to look at this and just get that figured out. So now what's the same? Well, if they lie in the same vertical line, they all have the same x value, which is -5. And then I would just take my a distance and add it and subtract it to 5. And my c distance and add it and subtract it to 5. This time that's a little bit different there. You got to write it like, how would I get there? So again, if I'm at 5 as far as a y value, plus 2 root 3 minus 2 root 3 plus 4 minus 4, right? So that's how that works. And then I still have the b at 2, and I can draw my ellipse. Okay, so there's graphing, pretty straightforward. We're going to run through a series of equation writing here in just a minute, and then a word problem to wrap it up. So equation writing, you know, I always attack this as basically like, you know, what's given, what do I need? If I don't have something, I go find it. That's kind of a simple approach to stuff. So just making a list of what I do know, you know, I can count the a distance is 4, the c distance, foci is 3, question mark, what is b? And then that's what my c-squared equation is for. I would think about this as, is it horizontal or vertical? That'll help later on. You know, just do a quick calculation. You don't have to go all the way down to b because the equation actually requires b squared. So just stop at b squared. And now I'm going to take my a, my b squared, plug them in. So equation writing can be really very simple. It's just a matter of you collecting your information. Sometimes there's a little side step, a little more work to do to get to that point. But again, what you're given, what you need, and then what's missing, go find it, right? Okay, let's do a couple more here. So again, same thing here. Now this time I have a b value. I don't have an a value, but I got a coordinate on the graph. And so when you have a coordinate in the graph, and we can tell again that it's vertical just by looking. What I'm going to do is use the coordinate. This is like a generic x comma y, and the b, and solve for a, because if I have x, y, and b, that's 3 of the 4 variables that are here. So we're going to kind of pop through the solving here. I'm going to just pop it all up quick so you guys can see it. So I'll plug in x, y, and b. Start cleaning stuff up. That's all the work here, and eventually get down to b squared. Again, you only got to go as far as b squared because that's all the equation requires, right? So go ahead and plot my b squared. Now a little bit of cleanup. This is kind of a little bit messy with it being divided by a fraction. So you can flip and multiply. That's a little cleaner look. That's probably the way I would write it. But you know, again, it's like what's missing? What do I have that'll help me? How do I go find it? Go find it. Plug it back in, write your equation. Okay. About 2 more to go here. So again, I would always check to see what type I have. With no visual here, you know, what does this tell me? Well, if my foci sit on the y-axis, then I know it's a vertical. So that's how I know that fact. And then eccentricity. Now the error here is going to be for you to say, well, eccentricity is a ratio of c over a, right? So I guess my foci, my c value is 4, and my a value is 5. But it's telling you here that actually your foci is 20. So that means this is a reduced fraction. That'd be really easy to miss. You know, you just like see this and go, hey, there's c, there's a, plot, man, I solved for b, but actually, no, this is c. Now, if that's the case, that means that's 25. So now I got my ABC kind of question again. I can go ahead and just, you know, basically do my solving over here quick, find my b squared, drop it in. Okay.